Good day. Today we're going to discuss the comparison, ratio, and root test. In this discussion, we will develop some of more basic convergence tests for the series with non-negative terms. Later, we will use some of these tests to study the convergence uh, of the Taylor series. So let's start with the comparison test. So we will begin with a test that is useful in its own right and it's also the building block for another important convergence test. So the underlying idea of this test, which is the comparison test, is to use the known convergence or divergence of a series to deduce the convergence or divergence of another series. So let's start with a theorem. So let the series of a sub k from 1 to infinity and the series of b sub k from 1 to infinity with non-negative terms, and suppose that a sub 1 is less than or equal to b sub 1, a sub 2 is less than or equal to b sub 2, a sub 3 is less than or equal to b sub 3, so on up to a sub k less than or equal to b sub k, and so on. If the bigger series, the summation of b sub k converges, then the smaller series summation of a sub k also converges. And if the smaller series, the summation of a sub k diverges, then the bigger series summation of b sub k also diverges. Okay, so in dealing with the comparison test, there are two steps required for using the comparison test to determine whether a series, which is the u sub k with positive term converges. The first one is guess at whether the series u sub k converges or diverges. Then after that, find a series that proves the guess to be correct. That is, if we guess that the series u sub k diverges, we must find a divergent series whose terms are smaller than the corresponding terms of the series u sub k. And if we guess that the series u sub k converges, we must find a convergent series whose terms are bigger than the corresponding terms of the series u sub k. So in most cases, the series u sub k being considered will have its general term u sub k expressed as a fraction. So to help with the guessing process, in the first step, we have formulated two principles that are based on the form of the denominator for u sub k. These principles sometimes suggest whether a series is likely to converge or diverge. We have to call these informal principles because they are not intended as formal theorems. In fact, we will not guarantee that they always work. However, they work often enough to be useful. And these informal principles are this one. The first one is the constant term in the denominator of u sub k can usually be deleted without affecting the convergence or divergence of the series. And the second one, if the polynomial in k appears as a factor in the numerator or denominator of u sub k, all but the leading term in the polynomial can usually be disregarded without affecting the convergence or divergence of the series. To understand more these informal principles, let's try to have our examples. Example 1, use the comparison test to determine whether the series converge or diverge. For our solution, according to the first principle presented in the previous slide, we should be able to drop the constant in the denominator without affecting the convergence or convergence. Thus, the given series, is likely to behave for our solution, okay, will likely to behave uh, with this series. Okay, you have the summation of 1 over the square root of k, okay, from 1 to infinity. So, uh, from the previous example, the previous discussion that we had, this series is actually a divergent using the principle of p series, where in this case rather rp is equal to 1/2. So from the concept that we discussed previously, this would be divergent in the concept of p series. Okay, where our p is equal to 1/2. Thus, we will guess that the given series diverges and try to prove this by finding a divergent series that is smaller than the given series. However, the series, which is the given, okay, does the trick, since we all know in this behavior, okay, that 1 over the square root of k minus 1/2 is actually greater than 1 over the square root of k. Okay, for k equals 1 or 2 and so on. So in this case, we could say that the we have already proved that the given series is a divergent series. The given series is a divergent because this this series is a divergent from the P series. Okay, so in other words, since using the second principle that the first principle rather, that uh, a theorem the theorem presented in the previous slide, that if the the given series is greater than the another series that they have similar, it means that they have a similar convergence. So that's why the given series is a divergent, since 1 over square root of k, the series of 1 over 1, the series 1 over square root of k from 1 to infinity is a divergent series. Okay, so let's have second example. Okay, so again, use the comparison test to determine whether the series converge or diverge. So in this case, according to the second principle presented in the previous slide, we should be able to discard all but the leading term in the polynomial without affecting the convergence or divergence. Okay, thus the given series will likely to behave in this case. So you have, okay, this would be this series will likely to behave with this series again. So you have 1 over uh, 2k squared from 1 to infinity. We just drop the constant, okay, which is the k. In this case, using the concept of the summation, we could have 1/2 of the summation of 1 over k squared from 1 to infinity. So, okay, In other words, this series will likely to behave with this series. In this case, we know from the previous examples that we had that 1 over k squared is a convergent series, okay, or convergent uh, uh, a convergent sequence. And since it's a convergent sequence, it's also a convergent series. So uh, in this case, the constant times the p uh, convergent p series, which is p is equal to 2. Okay, thus we will guess that the given series converges, and we are going to prove by finding a convergent series that is bigger than the given series. However, this kind of series does the trick because we know from the given fact that 1 over 2k squared plus k is less than 1 over 2k squared for k equals 1, 2, 3, and so on. So in this case, okay, therefore we could say that the given series converges. Okay, so what we did here is we are just going to look for the the series, okay, that is less than or greater than the given series, following the concept of the principles presented in the previous slide. So that's it. Now let's have the limit comparison test. In the past examples, we have principles 1 and 2 provided the guess about the convergence or divergence, as well as the series needed to apply the comparison test. Unfortunately, it is not always so straightforward to find the series required for comparison. So, we will now have to consider an alternative to the comparison test that is usually easier to apply. Okay, so this is the theorem. Let the series A sub k and the series B sub k with positive terms, and suppose that the rho is equal to the limit of k A sub k over B sub k, where k approaches to positive infinity. If the rho is finite and the rho is greater than 0, then the series both converges or both diverges. So to use the limit comparison test, we must find again first guess at the convergence or divergence of the series A sub k, and then find the series B sub k that support our guess. Okay, let's have an example to illustrate this principle. Okay, so use the limit comparison test uh, to determine whether the series converge or diverge. So we have the series, the summation of 1 over square root of k plus 1 from 1 to infinity. Okay, in the example, okay, so the principle 1 suggests that the series is likely to behave like a divergent p series. To prove that the given series diverges, we'll apply the limit comparison test with, in this case, okay, for our solution, in this case, we could have our A sub k is equal to 1 over square root of k plus 1. And our b sub k would be 1 over square root of k. So we obtain, okay, that the rho is equal to the limit of a sub k over b sub k from where k approaches to positive infinity. Okay, so in this case, we could have the limit of our a. So you have 1 over square root of k plus 1, okay, over 1 over square root of k from k as k approaches to positive infinity. So in this case, we could simplify this one. It could be the limit of, in this case, square root of k over square root of k plus 1. Okay, as k approaches to positive infinity. So in this case, we could divide the numerator and denominator by square root of k. Then we have the limit of 1 over 1 plus 1 over square root of k as k approaches to positive infinity. Okay, so in this case, we could have the limit of 1 is from as k approaches to positive infinity is 1. The limit of this one is also 1, and then the limit of this one is 0. So 1, so you have 1 over 1 plus 0, that's equal to 1 over 1, which is equal to 1. So since, okay, therefore, okay, since P is a finite and positive, it follows from the theorem that the given series diverges. Therefore, this one, the series diverges. Okay. Okay, so let's have this one. Okay, again, same instruction, but the series is 1 over 2k squared plus k as from 1 to infinity. So again, as in the example previously, in the principle 2, that suggests that the series is likely to behave like a convergent series. To prove that the given series converges, we will apply the limit comparison test. In this case, for our solution, our a sub k, our a sub k would be 1 over 2k squared plus k. And our b sub k would be 1 over 2k squared. So in this case, we could obtain from the formula that the rho is equal to the limit of a sub k, okay, over b sub k as k approaches to positive infinity. Okay, we could have, okay, it's equal to the limit of 1 over 2k squared plus k over 1 over 2k squared as k approaches to positive infinity. This is simply the limit of, we have 2k squared over 2k squared plus k, okay, as k approaches to positive infinity, which again becomes, if we are going to divide the numerator and denominator by k, that would become the limit of 2 over 2 plus 1 over k as k approaches to positive infinity. So in this case, we could have the limit of this one is 2, the limit is this is 2, and then the limit of this one is 0. So 2 over 2, okay, is equal to 1. Okay, since our rho is a finite and positive, it follows from the theorem presented previously that the given series converges, which agrees with the conclusion reached from the previous example using the comparison test. So in this case, it will say we are going to we had then proven that the series converges. Okay, so let's have this one. Uh, the series of the summation of 3k cubed minus 2k squared plus 4 all over k raised to 7 minus k cubed plus 2, okay, from 1 to infinity. So in this case, okay, the second principle, okay, the series is likely to behave uh, for a solution. Okay, the series would likely to behave the summation of, in this case, we could now we can now disregard the other terms. That would be 3k cubed over k raised to 7 as k approaches to 1 to infinity. And in this case, if we are going to divide the common factor of the numerator and denominator, this will become the summation of 3 over k raised to 4 from 1 to infinity. So in this case, we could clearly say that this series converges. Okay, from the previous discussions that we have, we could really say that in this case, this is a convergent series since it is a constant times a convergent, because take note that this would be 3, okay, summation of 1 over k raised to 4 from 1 to infinity. This is a convergent because our r here, our p here is 4, and this is a constant times a convergent series. Thus, uh, the given series is likely to behave convergent. Okay, and if we can now use the limit comparison to the series, okay, to prove that this is that this series is also a convergent. So for our rho, that's equal to the limit of uh, we have our this one, uh, 3k cubed minus 2k squared plus 4 all over k raised to 7 minus k cubed plus 2 all over you have 3 over k raised to 4 as k approaches to positive infinity. So in this case, we are going to simplify this one. Okay, simplifying this one, we could have the limit of, okay, so this is multiplied by this one. So that is 3k raised to 7 minus, that would be 2k raised to 6 plus 4 k raised to 4 all over you have 3k raised to 7 minus 3k raised to 3 plus 6 as k approaches the positive infinity. So in this case, we are going to divide the numerator and denominator by k raised to 7. That will become the limit So you have 3 minus 2 over over k plus 4 over k raised to 3 all over 3 minus 3 over k raised to 4 plus 6 over k raised to 7 as k approaches to positive infinity. So in this case, this is 0, this is 0, this is 0, this is 0. So you have 3 over 3, which is equal to 1. So since our row, this is a row, okay, is a finite and a non-zero, it follows from the theorem presented previously that the given series converges. So therefore, the series converges. Oops, converges. So that's it. Now let's move to the ratio test. The comparison test, okay, and the limit comparison test hinge to on the first making of guess, okay, about convergence and then finding an appropriate series for comparison, both of which can be difficult tasks in case where the first principle and second principle cannot be applied. In such cases, the next test can often be used when it works exclusively with the terms of the given series. It requires neither an initial guess about convergence nor the discovery of the series for comparison. So we're going to use the ratio test. So this is the theory for the ratio test. Let the series u sub k with the positive terms and suppose that the rho is equal to the limit of the u sub k plus 1 over u sub k as k approaches to positive infinity. So in this case, if the rho is less than 1, it converges. If the rho is greater than 1, or the p is equal to positive infinity, the series diverges. If p is equal to 1, the series may converge or diverge so that another test, okay, must be tried. So in this case, the we have now the another conditions. So if the rho is less than 1, it converges. If it is greater than 1 or equal to positive infinity, then it diverge. If it is exactly equal to 1, so it's either converge or diverge. So we are going to use another test to verify. Okay, let's have an example. So given the ratio test, determine whether use the ratio test to determine whether the following series converge or diverge. So we have the first example. So in this case, the series converges since we could have, in this case, okay, we could have the rho is equal to the limit of you have the formula u k plus 1 over u sub k as k approaches to positive infinity, okay, which is equal to the limit of you have 1 over k plus 1, okay, the next of this, remember that when we say k plus 1, it is the next element of this one over the 1 over k factorial as k approaches to positive infinity. So in this case, we could simplify this one. You have the limit of, you have the k factorial over uh, the quantity k plus 1 factorial as k approaches to positive infinity. Now, take note that the next term of this factorial is k plus 1. So in this case, we could have the limit of k times k plus 1 factorial over k plus 1 factorial as k approaches to positive infinity. So since we have a common factor in the numerator and denominator, we could we could divide that one out. So what remains is the limit of k as k approaches to positive infinity. So in this case, uh, there is something wrong that I have done here. Okay, so here to correct, you have the limit. In this case, you have k times, okay, if we are going to continue this one, you have k minus 1 factorial over, so here you have k plus 1 times the next of this one would be times k times k minus 1 factorial as k approaches to positive infinity. So in this case, we could now divide out some of the common factors in the numerator and denominator. So in this case, we could uh, divide out these terms. So what we have is you have the limit of 1 over k plus 1 as k approaches to positive infinity. So in this case, we could now have the limit of 1 is the limit of constant is the constant. However, in this case, the limit of k plus 1 as k approaches to positive infinity is 0. Okay, so in this case, not zero but infinity. So uh, you have 1 over infinity you have the limit of 1 over infinity is equal to 0. Therefore, as we can see, the row which is equal to 0 is less than 1. Therefore, we could now say that the series converges. Okay, so let's have another example. So you have the summation of k over 2 raised to k from 1 to infinity. So in this case, we could also say here that this is a series, the series is converges or the series converges because if we are going to have the the limit, so in this case for our solution, okay, so we have the the row is equal to the limit of u over u sub k plus 1 over u sub k as k approaches to positive infinity. So in this case, you could have, so we have here the limit of, you have the k plus 1 over 2 raised to k plus 1 over, you have k over 2 raised to k as k approaches to positive infinity. So in this case, we have the limit of reciprocal. You have the uh, k, okay, so you have uh, 2 raised to k times k plus 1 all over. So in this case, you have uh, you have 2 raised to k plus 1 times k as k approaches to positive infinity. These 2 raised to k plus 1 can be rewritten as the limit of 2 raised to k times k plus 1 over you have 2 raised to k times 2 times k as k approaches to positive infinity. So in this case, we could now divide out the common factor. Then the you have the constant 1/2, so we can now we can write the constant before the limit. So you have the 1/2 of the limit k plus 1 over k as k approaches to positive infinity. So in this case, here, so in this case, since you have 1/2 here, uh, this is equal to, okay, 0 plus 1 equals 0. Ah, infinity plus 1 over infinity, that is equal to 1. So you have 1/2 times 1 is equal to 1/2. So in this case, you could have the rho is equal to 1/2, which is again less than 1. So in this case, we could now say that the series converges. Okay, so let's have another example. So you have k, the summation of k raised to k over k factorial from 1 to infinity. So in this case, we could have here, let's have a solution here. We could have uh, the rho is equal to the limit of you have the u sub k plus 1 over u sub k as k approaches to positive infinity. So we could have, you have the limit of, you have the quantity uh, k plus 1 raised to k plus 1 over k plus 1 factorial over, you have k raised to k over k factorial as k approaches to positive infinity. So in this case, we could rewrite this one. So you have the limit of uh, reciprocal of this one. So you have k plus 1 quantity raised to x plus k plus 1 multiplied by k factorial all over, you have the quantity k plus 1 factorial times k raised to k as k approaches to positive infinity. So in this case, this one, okay, we know that this one, okay, can be expressed as k times k minus 1 factorial. In this case, this can be expressed as the quantity x plus 1 times k times k minus 1 factorial. So what, in this case, we can divide out the k factorial and the k times k minus 1 factorial. So what remains here is you have k plus 1, and here you have k plus 1 raised to k plus 1 can be expressed as k plus 1 raised to k times k plus 1. So k plus 1 and the denominator is another k plus 1, then it can be divided out. So what remains is you have the limit of k plus 1 raised to k over k raised to k as k approaches to positive infinity. So here you could have the limit of the quantity k plus 1 over k raised to k as k approaches to positive infinity. So in this case, this can be rewritten if we are going to uh, divide the numerator, okay, if we are going to express this one, okay, with a uh, separate ellipses, then you have the limit of 1 plus 1 over k quantity raised to k as k approaches to positive infinity. This will be equal to, okay, from the previous calculus that you have learned, this is actually, the limit of this one is actually E, the Euler number. So since the P, not the P, the rho is equal to E, and we know that E is greater than 1. Therefore, this series, okay, the series diverge, okay, diverges. So we have now answered that this series is a divergent series. So let's have another example. So in this case, okay, the this one, okay, for our solution, then you have the rho is equal to the limit of u sub k plus 1 over u sub k as k approaches to positive infinity. This can be written as, this case, you have the limit of the quantity, you have 2 times k plus 1, okay, quantity factorial over 4 raised to k plus 1 over, you have the quantity 2k factorial over 4 raised to k factorial as k approaches to positive infinity. So in this case, we could have, uh, using the reciprocal, you have the limit of the quantity, the quantity 2 times the quantity x plus k plus 1, okay, factorial, uh, here, times 4 raised to k over, you have 4 raised to k plus 1 times the quantity 2k factorial. This is not supposed to be factorial. As k approaches to positive infinity. So in this case, we can rewrite now our limit as the limit of, in this case, we can rewrite this one as, we have 2k plus 2 quantity factorial times 4 raised to k all over, this one can be written as 4 raised to k times 4 times the quantity 2k factorial as k approaches to positive infinity. So in this case, this can be rewritten as, okay, this is can divide out. So you have 1/4 of the limit. You have uh, the quantity 2k plus 2. Okay, we are going to expand this one. Okay, we're going to expand this one. 2k plus 2. The next one is 2k plus plus 1 times this one. You have 2k factorial over, you have 2k factorial as k approaches to positive infinity. So in this case, we can divide out. So what remains is you have the 1/4 times the limit of the quantity 2k plus 2 times 2k plus 1 as k approaches to positive infinity. So in this case, we could have that the limit of this one from your previous calculus, the limit of this one is infinity, and then the limit of this one is positive infinity, and the product of this one is also infinity. So infinity times 1/4 is equal to infinity, okay, positive infinity. Therefore, we could now say that since the rho, okay, is equal to positive infinity, we could now say that the series diverges. Okay, so let's have another example. So in this case, we're going to use again the um, the ratio. So you have for our solution, okay, you have our rho is equal to the limit of, you have you have 1 over, you have 2 times k plus 1 minus 1 all over, you have 1 over 2k minus 1 as k approaches to positive infinity. So in this case, we could have uh, we could uh, 2k plus 1 equals 2 minus 1 is 1. So you have, and then reciprocal. So you have the limit of 2k minus 1 all over, here you have uh, 2k. So here, this one, you have 2k plus 1. Okay, as k approaches to positive infinity. Now in this case, as you can see here, both we could have this is the limit of this one is 0 0, so you have 2k is equal to, so 2k over 2k is equal to 1. Therefore the limit is equal to 1. Now in the theorem, that if it is equal to 1, then it's either diverge or converge. Now let's have the integral test. So in this case, using the integral test, you have the integral of, you have dx, okay, over 2, okay, times x minus 1, okay, from 1 to positive infinity. Okay, and then get the limit, then you have the limit of the integral dx, okay, over 2 times x minus 1 from 1 to b as b approaches to positive infinity. So this is equal to the limit of the integral of this one is, uh, you have natural logarithm. So here you have the limit of, okay, 1/2 times the natural logarithm of 2x minus 1, uh, uh, as our b approaches to positive infinity. Okay, so from 1 to b. In this case, we could have, okay, the limit of this one is equal to positive infinity. So positive infinity. So in this case, both we could now prove that the series diverge. Okay, diverges. So in this case, both the comparison test and the limit test comparison test would also have, we could also use, okay, we could verify using the uh, comparison test and the limit comparison test. Okay, so let's have the root test. So in cases where it is difficult or inconvenient to find the limit required for the ratio test, the next test is sometimes useful. So since, uh, the if the previous test is very difficult, then we're going to use the root test. So let the series u sub k with positive terms, and suppose that the rho is equal to the limit of the kth root of u sub k as k approaches to positive infinity is equal to the limit of the quantity u sub k raised to 1 over k as k approaches to positive infinity. So if the rho is less than 1, the series converge or converges. If p is greater than 1 or p is equal to positive infinity, the series diverges. And if the rho, not the p, the rho is equal to 1, the series may converge or diverge. So the another test must be tried. Okay, so let's have example. So use the root test to determine whether the following series converge or diverge. So number one, you have the summation of the quantity 4k minus 5 all over 2k plus 1 raised to k from 2 to infinity. So in this case, we could have that the the series is actually diverge. Okay, to show that, okay, for our solution, we could have that the rho is equal to the limit. So you have the quantity u sub k raised to 1 over k as k approaches to positive infinity. So this is simply equal to the limit of, you have 4k minus 5 all over 2k plus 1 as k approaches to positive infinity. which is simply equal to, this is equal to, this is the limit of this one is 0, this is 0, so you have 2, 4k over 2k is equal to 2, since k over k can be cancelled out, so 4 divided by 2 is 2, so this is equal to 2. And as we can see here, our p is equal to 2, which is greater than 1. Therefore, we could say that the series diverge or diverges. Okay, so okay, let's have this one. Uh, the summation of 1 over the natural logarithm of the quantity natural logarithm of k plus 1 raised to k from 1 to infinity. So in this case, okay, as we can have our solution here, in this case you have the rho is equal to the limit of the quantity u sub k raised to 1 over k as k approaches to positive infinity. So in this case, you could have the limit of 1 over the limit, not the limit, the natural logarithm of the quantity k plus 1 as k approaches to positive infinity. So in this case, using the concept that you have learned in your previous calculus, then the limit of this one is equal to 0. Then since our rho is equal to 0, which is less than 1, therefore we could say that the series, okay, converge rather, converges. Okay, so that's how we are going to show whether the series converge or diverge. Okay, thank you very much.